So the format of today, we have 5 sections which sort of cover everything that could be on your midterm. So in the beginning we have the properties of things like expectation, variance, covariance. Then we'll talk about modeling, loss functions, and this idea of gradient descent. We'll then talk about the meat of the course, which is linear regression, so the normal equations, regularization, ridge regression, lasso, where we come up with these normal equations. We'll also talk about things like the bias variance trade-off. What does it mean when we increase or decrease lambda? And we'll wrap up by talking about logistic regression and classification, things like precision and recall, linear separability, the sigmoid function, and so on and so forth. Okay? So just a disclaimer, this is not necessarily a comprehensive review of the topics. There might be things in here that aren't on the exam, and there might be things on the exam that aren't here. Okay, so this is not a guarantee that this is solely what's on the exam. Okay, any questions logistically with what's going on? Great. Also, just a quick point on notation. A lot of people pointed this out on Piazza. In past semesters, we used phi as our design matrix, but in this semester, we're using x for that. Okay, so in these slides, at any point when you see x, it means an n by p design matrix with just all of your data points. Okay, but to my understanding, in lecture, you will also have seen x being referred to as just a single vector. Okay, so you need to sort of know, depending on the context, what exactly does x mean? Is it a vector or is it a matrix? But in these slides, big X will always mean a matrix. Cool? Okay, so now I think Alan will start with probability.
Hello. So there's a post on Piazza at 961. We'll be answering Piazza questions live. So feel free to post if you're not, like, if I don't see you or anything. Okay, so first, probability. So for this review session, we'll mostly just be going over expectation, variance, and properties, and then do some practice problems related to those. So for expectation, so we define expectation as the sum of x times the probability that x equals x. So that's this formula here. Oh, that's not what I wanted, but okay. Yeah, so that's that formula. So the variance is the expectation of x minus the expectation of x squared, and then you can do a simple derivation using linearity of expectation. That's the same as expectation of x squared minus expectation of x squared, where the squared is outside the expectation. And then the standard deviation is the square root of variance, and sometimes we like using standard deviation instead of variance because standard deviation is in the same units as the variable itself, while variance is in the units squared. And then covariance is defined by expected value of xy minus expected value of x times expected value of y. And that's like a generalization of variance. So if you like plug in covariance of x with itself, you'll get the same formula as variance of x. Okay, any questions on this slide? Okay, so here are some important properties. These are like really good cheat sheet material if it's not on the reference sheet already. So first is linearity of expectation, which states expectation of x plus y, and then equals expectation of x plus expectation of y, so you can bring the plus outside the expectation. And then you can pull constants out. So expectation of ax equals a times the expectation of x. And then you can use linearity of expectation whether x and y are independent or dependent. And yeah, so for variance, variance of x plus y is variance of x plus variance of y plus 2 times the covariance of x and y. So you'll notice like there's an extra 2 times the covariance term that wasn't there like when we were doing expectation. So if x and y are independent, you can see down here that the covariance is 0. So that means that we can get rid of that 2 times the covariance term. And then we just left with variance of x plus variance of y. Yeah, and then for scaling and shifting, so when you add a constant to the variance, it doesn't affect the variance. And then when you multiply by a inside the variance, you have to pull out a squared instead of just a in the case of expectation. Yeah, any questions on this slide? All right, so we'll go into our first problem. So we have some model y equals x beta plus epsilon, where x beta are non-random constants and epsilon is a random variable. And we know expectation of epsilon is 0 and the variance is sigma squared. So give you like a few minutes to do this one. It's on the post at 961. What? Alright, anyone one more time? Okay. So the slides have been posted on Piazza Post at 961. So if you want to follow along. Okay, so for this question, the key is essentially that since x and beta are non-random constants, their product is also a constant. So, and then epsilon is the only thing that's random. So, if we're trying to find the expectation of y, then that's the same thing as the expectation of x beta plus epsilon by definition. And then we can apply linearity of expectation to separate, put the plus outside the expectation. And then we're given that expectation of epsilon is 0, so that's 0. And then the expectation of x beta is just itself because it's a constant. Any questions on part A? Okay. So for variance, again, the key is that realizing that x beta is just a constant. So the variance of y is the variance of x beta plus epsilon. And then if you go back to this property over here, where we're saying if we add a constant, it doesn't affect the variance. So here we're doing variance of a constant plus epsilon. So you can just take out the constant. So you're left with just variance of epsilon, and that's sigma squared. Okay. Any questions on B? All right. Okay, so let's spend a couple more minutes on this one. Okay, let's go over this. So for the first one, 8, we're asking what's the expected value of x, and to give you some values and some chances. So we can use the definition of expectation, which is the sum over all possible values of x times the probability that it takes on that value. So that's really not good. Okay, I'm just gonna look at. Okay, so here we have 3 values: -1, 0, and 1. So -1 occurs with probability p squared. So this is where this negative p squared comes from. 0 occurs with probability 2p times 1 minus p. So since you're multiplying by 0, this becomes 0. And then for the last term, it's 1 with probability 1 minus p squared. So this is 1 minus p squared times 1. So if you simplify that out, you get 1 minus 2p. Any questions on this one? Okay. So for the next one, we're given three independent random variables, and we're given the variance is sigma squared, and they have the same probability distribution, so that means they all have the same variance. And then recalling the property from this slide, where if they're independent, then we know the variance is sum. So here we can just sum up these 3 variances. So this is the same as variance of x plus variance of y plus variance of z. And then since we know that they're identically distributed, each of these is just sigma squared. So the total is 3 sigma squared. Okay, any questions on this? Yeah. Not necessarily. It depends on the distribution of which one. So the question was, what happens if they're not independent? It might be anything. Like, you don't know what it would be. It depends on like the covariance between the two random variables. So like, you can't guarantee that's any of these. Any other questions? Yeah. Yeah, so in this scenario, we're not multiplying by a constant because we're just saying that these separate into 3 different variances. If you had something like variance of 3x, then you can say that that's 3 squared times variance of x. But like, we don't know y and z, they're not the same random variable as x, so you can't say that this is variance of 3x. So that's different from, like variance of 3x is different from 3 times variance of x. Yeah?
That's because, well, to answer your question, it's because x is not equal to y, and it's not equal to z. They're different random variables, so you can't just correlate them into one random variable.
Yeah. That, like, they're not the same random variable. Like, they have the same distribution, but they're not the same random variable because, like, one could come up differently from the other one. Okay, we're gonna move on. Feel free to call me if you have any questions.
All right. I'm going to make sure I don't talk too much into the microphone, otherwise it blinds your hearing. Okay. So, all right. Okay, so we're going to talk about modeling and gradient descent now. So essentially, after midterm 1, we started talking a lot more about loss functions, and we talked about the idea of modeling. And we're trying to model something that occurs in real life. So we usually use a loss function, and the loss function is a function that characterizes, as what's in the term, a loss or some error between our true value and the predicted value. So the true value is something in nature, and it's something that already exists, and we're using a function to model that value. And it's important to note that a loss function is characterized not only by the model parameters, so not only by like what you guys learned in class with betas, but also the choice of your model. So am I using a linear model? Am I using, for example, a polynomial or things like that? So loss function measures a loss for a particular observation, and then empirical risk is averaging the loss on the training set. So the empirical risk is like the average loss over a bunch of data points. Okay. And here are some common loss functions that we talked about in class. If we didn't talk about all of them, we talked a little bit about each one briefly. So we have L1 loss, which is basically like an absolute value. We have L2 loss, which is what you guys see most frequently, which is squared loss. And then we have Huber loss, which is kind of a combination of both. And the way to think about Huber loss is if you've seen kind of the loss function, around the center it looks like squared loss, but as you go further and further away from the center, it starts to look a lot like L1 loss. Okay, so you kind of get the benefits of both. And as we saw, there's trade-offs between each one of these loss functions with respect to outliers or with respect to extreme data points. Okay, any questions about just loss functions in general? Yeah. Yeah, so L2 loss, if you remember, is sensitive to outliers, right? And L1 loss is, so if you see L1 loss, it's like an absolute value bar. If it's an absolute value graph. So it's harder to take the derivative. So when you guys learned about how to solve for the derivatives and finding the minimums, because L1 loss is not differentiable, you have to resort to other techniques. Okay. Okay, so we saw how to minimize risk. So basically the idea is you have this loss function, and you're trying to take the derivative of the loss function and set it equal to 0 at a high level. And we say that's your favorite procedure. But the intuition behind that is we're trying to find our parameters, right? So we're trying to find the beta values that fit our data really well, so that way we can predict on those values that they're closer and closer to the values, the true values, right? So usually we're interested in convex loss functions, right? So convex loss functions are loss functions that have global minimums because they're easy to take the derivative of. And then when we talk about like gradient descent, when we have a convex loss function, we are guaranteed to find the minimum, right? The global minimum. If we don't have a convex loss function, we can get stuck in those local minimums, and then we don't know if we found the actual global minimum. Okay, so as I mentioned, you take the derivative or the gradient, you set it equal to 0, and you solve for the optimal parameters. Okay, so now we're going to talk about what happens when you can't take the derivative of a loss function, right? So that's where gradient descent comes into play. Okay, so the key high-level idea for gradient descent is you do this iterative procedure to find the gradient. You use this iterative procedure step by step to find an estimate for the minimum. So when you take the gradient of a loss function, we saw that we have to do gradients, and essentially if we look at this update rule here, right, if you notice that we're moving the negative, so when we take the derivative of the loss function, we're moving in the direction opposite the gradient. Okay, so the reason we move in the direction opposite the gradient is because that will help point us towards the global minimum. Okay, and we'll see a picture in future slides that will help clear things up. But essentially, the idea is we have some BT, which is our estimate for beta at time t, and we want to find an improved version at time t plus 1. Okay, so our update rule helps us update that beta value, where we use the beta value at time t, then we evaluate the loss function using beta t, and take the derivative of it, and then we move beta t in the direction of the gradient. And then we have some alpha, which is the step size. Okay, and that determines how large steps are, and then we saw also in class some implications of how to basically tune alpha, so that way we don't jump over the global minimum or jump around a lot. Okay? So any questions about like the intuition of gradient descent? Yes?
Can you just repeat how you describe the function?
This function here. The update, yeah. So remember with gradient descent, it's an iterative procedure to find the right beta value, right? So we have some beta t, which is the beta at time t, and we're trying to find beta at time t plus 1. So our update rule says that we need to move beta at time t in the direction of the gradient of the loss function using beta of t. So we're moving it in the direction opposite the gradient, which is why we have this negative here. So if your gradient is positive, we're going to basically lower the value of beta t. And if our gradient is negative, we're going to increase the value of beta t. And I'll explain why we do this on a picture. It'll make more sense. The picture's on the next slide. Yes? Yeah, so the question is, how do we optimize alpha? So we don't talk about how you optimize alpha in this class, but there are procedures that you can use. So for example, one procedure is like as every iteration, you basically have alpha decrease exponentially. So if you use alpha, so at the very beginning, alpha will be like its largest value, right? And that's to allow for like more exploration, basically to find the global minimum. But as you get closer and closer, as you run more iterations, you don't want your alpha to become too big. Otherwise, but as you get closer to the minimum, you can jump over the minimum and basically jump around. Okay, we don't talk about how we tune alpha in this class, but that's just kind of a high-level intuition of how you would do. Okay. Yes?
In the mover loss function, can you just go back one? Where do you get the half from?
This thing?
No, the half on the one above
Oh, half. That's just the definition of the Huber loss function. Yeah. So we didn't actually talk about like where it comes from, but the Huber loss function is defined this way. Okay. Any other questions? Yes.
So usually we use the formula with the summation, right?
Yeah. So this is the loss function for one data point. Yeah.
So for MSE, like the reference table on Piazza posted for the Wisdom tomorrow, we do the expectation of the x and the beta. So can you explain like when do we use the summation formula, when we use this, and when do we use the formula for the expectation?
Yeah, so usually you use the summation if you're trying to find the average loss. So this is the loss function in general for y. So y is our predicted, or y is our true value of our data, and y hat is our predicted value. Now, usually when we're doing gradient descent, or when we have a bunch of data records, we want to find the average loss, which is why we sum over the loss and then we divide by n. So n is the size or the number of data records we have. Does that make sense? Okay. Okay, so if we look at the picture for gradient descent just at a high level, so as I mentioned, if your gradient here, in this case, if your gradient is positive, we see that the global minimum is here. So logically, we would want to move our beta vector to closer to, so we want to move it in the direction opposite the gradient, right? So since it's positive, we want to move our gradient vector closer this way. Okay? And then if our gradient was negative, it's a bad line, we'd want to move our beta vector closer to the right. So we want to increase the value of beta. Okay? So from like a high level, that's basically the reason of why we move in the direction opposite the gradient. Okay? And these are just some considerations to think about, but if alpha is too big, we talked about how if alpha is too big, basically it will, if you think about what alpha is doing, it's scaling how much you change your beta value. So if alpha is too big, you're going to scale it, you're going to basically change your beta vector too much, and you might jump the minimum, so you might jump the minimum. And if alpha is too small, what's going to happen is you're basically not going to change your beta value too much. And as a result, you're going to have to do more and more iterations of gradient descent. Okay? Okay, any questions about this slide? Yes?
In that notation, is the L implicit?
Yeah, it's a typo. So this should be like L of beta t. Gradient. Yeah, sorry about that.
And then this is the derivative.
Yeah, this is the derivative sign. We're taking the derivative with respect to beta. Okay, yeah, so just quickly, there's some variations of gradient descent that we kind of touched upon. So we have the standard or batch gradient descent, which is using all n data points when computing the gradient. Gradient of this loss function. Okay, and we have stochastic gradient descent, which we randomly choose one single data point and we compute the gradient using only this data point. And some benefits of that is we're only using 1 point to update our beta value, so it's much quicker, right, than summing over, taking the gradient of every point. But it also approximates, it's an approximation. So you might need, most likely, you're going to need more iterations to reach the optimal beta value, right, in that case. So there's always a trade-off. But stochastic gradient descent is useful in terms of its quickness. And then we have mini batch gradient descent, which is just you randomly choose b points to compute the gradient on. So it's stochastic gradient descent, but basically you have b points instead of 1 point. Okay. Yes?
When you say you randomly choose one data point, do you choose it with replacement or without, or does it matter?
I believe it doesn't matter, but I'm not 100% sure. I'll get back to you on that. Yeah. Okay. Yes?
So with every step, we choose a different point, right?
Yeah. Because you're randomly doing it, so the question was with every step, are we choosing a different point? Because we're randomizing it, we might choose the same point in 2 iterations, but if we have a bunch of points, then it's very unlikely that we get the same point over and over again.
You choose every step.
Yes, every step. Every update, we choose a different point. Or we randomly choose a point. Yes? Yeah, that's a good. So the question was, do we create a new function using those points that we choose? And like, what are the purpose of the points? So remember that the average loss in general is like a sum of I equals 1 to n of the loss function between y and y hat. And then we usually do the average, right? So essentially, instead of summing up all till n, we're going to only choose like b, or we're only going to choose like 1 point, okay? So you can think of it as like, if I'm doing stochastic gradient descent, I'm not really doing an average anymore. I'm just choosing the loss of 1 point and then updating my gradient based on that. Okay, yeah, question? Okay, what this is saying is it approximates like the standard batch gradient descent algorithm. Because the standard batch gradient descent approximates, in standard batch gradient descent, we're computing the gradient using all the points. So in stochastic gradient descent, we're computing the gradient using like 1 point. So it's approximating the gradient. It's approximating computing the gradient using all the points. Yeah, we don't use all the points. So like this is done in standard gradient descent. Okay, so let's move on to some problems. So let's spend about 3 to 4 minutes on this question, and then we'll reconvene. Move on.
Review of how you come up with this.
Wait, how you come up with it? You just take the derivative, right? Wait.
If you're driven to the right hand side, you go to 0 and you see that the optimal C is the one.
Just take the derivative to the right hand side?
With respect to C.
Okay.
That should be. Yeah, with respect to C.
And show that it's equal to the mean? Okay. she has a question. Okay, we're gonna move on. Okay, so basically we have the set n data points, and we know that the average is here. And the question is the sum of the loss with the mean as our, so this is a concept model, but basically if we use x bar to represent like our beta, is the sum of the losses going to be less than or equal to the sum of the losses with any c? Is that true? If we use mean as our beta value, is that true or false? So how many people say true? Okay, cool. So it is true. Okay. How many people would like a derivation for like why that's true? Okay, cool. So an easy way to see that is, let's just take the derivative of the right hand side with respect to c. Okay? So I'm going to take the derivative with respect to c, this function, and we're going to try to show that c is equal to the mean. Okay, so by derivative rules, we can move the derivative inside. Okay, and we have that this is a sum from I equals 1 to n of 2 xi minus c. Okay, and then we multiply by -1 because we take the derivative of xi minus c, which is -1. Okay, and then now we can split up some terms. So if we take a look at, I'm going to move the -1 on the outside for a second. So -1, and then now I can move the sum inside. So I have the sum from I equals 1 to n of 2xi, and then I have minus the sum from I equals 1 to n of c. Okay, everyone following so far? Okay, so now I'm going to set this equal to 0. Okay, and then I can just divide the -1 over, so the -1 doesn't matter. So I have I equals 1 to n of 2xi minus the sum from I equals 1 to n of c, and I set that equal to 0. Okay, so this term becomes n times c, right? Because I'm summing over c n times. So I have 2 so 1 to n of xi minus nc is equal to 0. Okay. And then what I can do is I can move the c over. So I have xi is equal to cn times 2. I think I'll distribute the 2, yeah. Sorry. Okay. So let's see, if I distribute the 2, I should have a 2 here. And a 2 here. Yeah. So I forgot to distribute it here. Okay, so we'll have a 2cn. So if I divide the 2 over, I'll just have the sum from I equals 1 to n of xi is equal to cn. And then now if I solve for c, I have c is equal to the sum I equals 1 to n of xi over n. So this is the sum over all the xi, and I divide by n, which is the average. So this term right here is the average of, yeah. So this is the average of all the x's. Okay. Is that clear to everyone? Okay. Okay. So let's take like a minute and just go through this problem. So now we have the absolute loss. And we're trying to see if the statement is true. So take like a minute, and then we'll rehash. Okay. Yeah, I'm not going to do the next problem either. Let's move on. Okay, let's reconvene. So I know that probably wasn't enough time, but does anyone, so how many people say true? How many people say false? Okay, so it is false. Okay, so I won't go through a derivation right now because we're running a little bit short on time. But essentially with absolute loss, the parameter that basically minimizes the loss, so the beta value that minimizes the loss will actually be the median. Okay, so I'll go through, if you have any questions, when the next person is lecturing or at the very end, if we have some time, I can go through a derivation. Okay, so let's just do this gradient descent problem real quick. So this question basically is comparing stochastic gradient descent to the normal gradient descent algorithm. Okay, so let's just go through it together. So essentially we have stochastic gradient descent. We know that it's very similar to normal gradient descent, except that the gradient of the loss function is computed on a random sample of the data, right, instead of the entire data set. So which of the following are true? So A, at a particular iteration, stochastic gradient descent will often update theta more accurately compared, so in this class, in this semester, the theta was equal to beta. Okay, so stochastic gradient descent will often update theta more accurately compared to an update with regular gradient descent. How many people say true? Or how many people think this is true? How many people think it's false? Okay, cool. So it is false because stochastic gradient descent will most likely update it to be an estimation of the true beta value. Okay, for a convex loss function, a single step of gradient descent always decreases the loss. True? False. Okay, so it is false. And the reason why is because it also depends on our alpha value, right? So our step size, right? Okay, for a convex loss function, a single step of stochastic gradient descent always decreases the loss. Is this true? False? Okay, so it is false. And the same reason why is because of our alpha value, right, our step size. Okay? So now D, suppose it takes t seconds for one update of regular gradient descent. Stochastic gradient descent can usually perform more than one update in t seconds. Is this true? Okay, false. Okay, so it is true. So the reason why it's true is because we're doing stochastic gradient descent performs the update only on one point, right? So we can perform more updates in the t seconds than normal regular gradient descent. Okay, and obviously it's not under the above because we chose one. Okay, cool. So I'm going to hand it off to Suraj, who's going to talk about linear regression.
I'll just state that he was watching hockey while presenting, but okay. Why not? They deserve to know. Okay, so now we'll talk about linear regression. I'll move through it relatively quickly just because we're pretty short on time. So just a little review on some of these gradient identities that you probably went over in discussion. I wouldn't say they're too important, but just something to keep in the back of your mind. So the gradient and in all of these, we're assuming that we're taking the gradient with respect to x, I guess you could say. And a and x are both, little a and x are both n-element real vectors. So the gradient of a transpose x is just a, the gradient of x transpose x is 2x, and the gradient of x transpose ax is a plus a transpose x. In this last case, when a is symmetric, this actually equals 2ax. And the reason this is important is because when we do the calculus derivation to the normal equations, that comes up, essentially. So you sort of need to know that. Yeah? Positive semi-definiteness relates to convexity. All I can say is if it was covered in lecture, it's technically in scope. Any other questions? Great, okay. So to motivate where linear regression comes from, first let's just start with the problem. suppose we're given a set of points, x1, comma y1, x2, comma y2, so on and so forth, and you want to fit a line y is equal to beta 1x plus beta 9. Okay, so essentially you're just given a scatter plot of points, and you want to find the y is equal to mx plus b that goes through it the best, roughly speaking. Okay, and so our model is y is equal to beta 1x plus beta 0. And if we're using mean squared error, so in other words, mean L2 loss, our objective function would be something like this. 1 over n times the sum for all of our points of the actual y value minus the predicted y value. Okay? And so you can write this out even in more detail if you want to. You could have y1 minus beta 1 x1 minus beta 0 squared plus y2 minus beta 1 x2 minus beta 0 squared, and so on and so forth. And you do that over all of your points. And we're taking the average of that because we want the average L2 loss for over all of your points. So any questions with this? Okay. Notice I haven't talked about beta or x or y being vectors at any point here. We're just talking about scalars here for now. Okay? But then now what I want to do is try and rewrite this in vector form. Okay, so we'll introduce these two vectors, I guess, and one matrix. So our beta vector is our vector of weights, as you know it now, and y is a vector of our observations. This matrix X is what we call our feature or design matrix. Okay, and the reason it's defined this way is if I take this multiplication of x and beta, well, x in this case is 1x1, 1x2, blah, 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 1xn. And then I multiply this by beta 0 and beta 1. Right, notice here I've written it as a row vector transpose just because it's kind of hard to write tall vectors in a single line. I do this multiplication. What do I get? Well, I get beta 0 plus beta 1x1, beta 0 plus beta 1x2, and so on and so forth. Is that clear? But these are just my predicted y values. So that's where the idea of modeling y with x times beta comes from. Is that clear? So our model y hat is just x times beta. And I think the way you might have seen it in class talks about it like the expectation of y given x is x transpose beta. People have seen this, right? So the difference between the x I'm talking about here and the x we have up here is that this is a single point. Okay, so when we're talking about the expectation of y given x, that x is a single vector, it's a single point, and we're trying to predict a new value given that we've already trained our data. Does that kind of make sense? So this x we're talking about here, you can think of as being your training data set, and over here you're trying to predict it on some new data point that that hasn't seen your model before. You're actually doing some prediction. Okay, and yeah. No. So if x is defined to be your feature matrix, you do not have to say x transpose. Yeah. The reason you see x transpose over here is because in this context, and I'm pointing to the thing at the very top, is because x in that context is a vector, and beta is also a vector, and so in order to get a scalar out of that, you need to transpose one of them so you can do the inner product. So you just have to switch between the contexts, and you have to know when are they talking about x as being your design slash feature matrix, and when are they talking about x being a single new test point. Yeah? No, so if you look at the reference sheet that was posted on Piazza, this form up here is what will be provided to you. Yeah, I will admit it's slightly confusing. We were also confused before putting this together. It's okay. And so back to this idea here, the loss function we're using, again, is the mean squared error, right? Mean L2 loss. And notice, when we look at y minus x beta, that just gives us y minus beta naught minus beta 1 x1, and so on and so forth. And that should be y1, this should be yn. And so if we square that, we get the mean squared error that we had over here, and multiply by 1 over n out front. And that sort of tells us why our loss function in terms of beta is 1 over n times the L2 norm of y minus x beta squared. Is that clear? We take our actual vector y, subtract it from our predictions x times beta. That gives us essentially a vector of y1 minus y1 hat, dot, 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 through yn minus yn hat. Take all of those elements, square each of them, sum them, and multiply that by 1 over n, and that's our mean squared error. Cool, here and then here. That means we're using L2 loss, so the squared loss, i.e., so for example, just to be a little explicit, like, it just means like y minus y actual quantity squared, if that makes sense. Yeah?
Why isn't it yi minus beta 1x plus beta 0? Because top part, isn't that the top product beta 0 x1 plus beta 1?
So is the question, why is this not plus? Over here, like why is this not plus? It's because you have to distribute the negative, right? So we have yi minus yi actual, or yi predicted, so y hat I guess. But then y hat I can just replace with beta 1 xi, and there should be I there, I guess, plus beta 0. But then I distribute the negative sign, so you get the two negatives. Okay, cool. We'll move on because, again, we have a lot of material to cover. And so there's the solution to the normal equation, using these gradient rules that we talked about at the beginning. You take the gradient, set it equal to 0, and solve. Not going to do all of that right now, but it all exists in the discussion 7 walkthrough video. So if you watch that, you'll see me going through that essentially. There's also the solution to the normal equation using geometric intuition, which we also talk about in the discussion 7 walkthrough, but I'll talk a little bit about that here. And so this error vector is the difference between our actual y value and our predicted y value. So we have y minus, this diagram is a relic from previous semesters where we used phi instead of x and theta instead of beta. So this should be x beta. Essentially, what you'll see is that the way to minimize this error vector is picking an error vector such that it's orthogonal to the column space of x. Okay, and so writing out that relationship, you get x transpose y minus x beta should be 0, right? Because if two vectors are orthogonal, their dot product should be 0, and A transpose B is just the standard dot product of two vectors A, B. Well, that generalizes to matrices as well, and you see that this multiplication should be 0, and you solve and you'll get your fancy x transpose x inverse, x transpose y. Okay, but again, this will be in the discussion solutions and walkthrough video, so we won't talk too much about it here. But any questions? Okay, and so then comes the idea of regularization. Okay, so there are some issues with ordinary least squares, which is just the loss function you've seen before. OLS is the solution to this thing. Okay, and so again, this is something that I'm sure they covered in lecture. The solution doesn't always exist. So for example, if some of your columns are linearly dependent, or you have more features than you have actual observations, your matrix X will not be full rank. And that implies that your matrix X transpose X will also not be full rank. And so in that case, you can't invert X transpose X. So the solution, which we all know and love, given by X transpose X, inverse x transpose y. Well, if x transpose x is not full rank, you can't invert it. So that's a problem. And we didn't really emphasize this too much this semester, but sometimes there's numerical issues with inversions. But the main reason we want to use regularization is to prevent overfitting, which is what we're going to start talking about. Yeah?
If there's problems with inversions, why couldn't we solve x transpose y is equal to x transpose x or beta? We should get.
So you're saying, like, why don't we just estimate x transpose x beta is equal to x transpose y? Yeah, so that's also a potential solution. But I'm just listing reasons why we might consider doing regularization. And again, the numerical issues thing isn't something we really focused on this semester. Yeah?
I mean, if x transpose x is not invertible, that means it's not onto. So it's not full rank, so it's not onto. So you can't. There's not necessarily a solution.
Yeah, or there could be infinite solutions, right? And so what we want is a guarantee that there's a unique solution. And that's something that we get with ridge regression, okay, which is what we're going to start talking about. But essentially, in order to fix all of these problems, what we do is we add this penalty on the magnitude of beta. Okay, and conveniently, it solves a lot of these problems for us. So the thing is, we have a choice of what vector norm to use when we're adding this penalty. Okay, so there's two types, and they correspond to two different types of regularization. So the one that you've probably seen more is ridge regression, and that's when we use L2 loss. Okay, so we have the L2 norm here, right? So we're taking all of the elements in our beta vector, squaring them, and adding them up. Okay, and there's also lasso regression, where we use L1 normalization, or the L1 norm for beta, and there we take the absolute value of every element in beta and sum that up. Yes? Oh, fix the numerical issues? Honestly, I don't have a good answer for that, but I'll be real with you. This is just a point that I had last semester because they talked about it last semester. I wouldn't worry too much about that. Okay. So any questions with the difference between ridge and lasso regression? Yeah?
Wait, so is lambda just like an arbitrary constant that we're bringing in?
So good question. Where does lambda come from? Yeah, and so that represents the amount, essentially, to which that we care about beta not being too big. Okay, it's the penalty on the size of beta. Okay, and a question that comes up, how do you pick the best value of lambda? Well, that's something that Neil will talk about when we get to cross-validation. Okay, but essentially you just try out a bunch of different values of lambda, see which one works best for you. Okay, so first we'll talk about ridge regression. So again, this is the new optimization problem I guess we're trying to solve. And the solution to this can also be determined just by using those gradient rules that we're familiar with. And again, this is also part of a discussion walkthrough video. But what happens is it looks very similar to the solution for OLS, ordinary least squares, but there's this plus lambda I term here. Okay? And so, as I mentioned, lambda represents the penalty on the size of our model. And unlike ordinary least squares, this always has a solution. Oops, sorry. And also notice, if you let lambda be 0, this is the exact same as ordinary least squares. Yeah?
In the regression function,
Yeah.
it's the two changes for both.
Yeah. Sure. The top one means that it's squared. And the bottom one means that we're using the L2 norm. So, okay, essentially what this means, so pretend beta is a vector that looks something like beta 1, beta 2, dot, 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 beta p. Let's just say we have p features. What this thing means is just beta 1 squared plus beta 2 squared plus dot, dot, dot plus beta p squared. Does that make sense? Yeah. Yes. So when we add lambda I, what happens is x transpose x plus lambda I becomes positive definite, and there's a property that all positive definite matrices are invertible. Correct. There's that whole list of equivalent theorems and, I don't know, Math 54 or something, and a matrix being full rank and a matrix being invertible. Those are equivalent conditions. Yes? Yeah. Yeah. There won't be a closed form solution. Yeah, we're about to get to that. Yeah. Okay, but so essentially this is what happens with ridge regression. If you let lambda be 0, it essentially turns back into ordinary least squares. And then the question is, what happens when you vary lambda? And again, that's something Neil will talk about very shortly. Okay, then there's the idea of lasso regression, where the difference is over here, we're using the L1 norm. And just to write it out explicitly, again, pretend beta is a vector with beta 1, beta 2 through beta n. What this fancy thing means is just absolute value of beta 1 plus absolute value of, I guess, beta 2 plus ... absolute value of beta n. Okay? And one of the cool things about lasso is that it encourages sparsity. And what that really means is that it encourages a lot of the weights in our feature vector, so a lot of the entries in beta to become 0. Okay, and why exactly that is, I think, is outside of the scope of this course, but I'm about to show you a cool little diagram that might add some intuition to that. Okay, and since it sets some of our weights to 0, it does a little bit of feature selection for us, right? If it assigns the weight of 0 to a particular feature, right? So if it assigns the weight of 0 to a particular beta I, it's telling us, hey, in order to minimize the loss function, you don't need to use this feature. So it's doing a little bit of feature selection for us, which is cool. Okay? And so notice before with ordinary least squares and ridge regression, there's this nice closed form solution we could write. Well, I don't know if you'd call it nice, but you could write it. And then now for lasso, there actually is no closed form solution. Actually, okay, that may or may not necessarily be true, but for our purposes, you're never going to look at a closed form solution for beta. And so you have to use some sort of numerical method, like Neil talked about, such as gradient descent. Cool, which will numerically help us optimize the function. Sound good? Yeah.
Do you ever use L1 for the first part?
Could you? Yes. In all realistic applications, no, not really. Yeah, and that actually brings up a good point. We're talking about L2 and L1 regularization, but the loss function, or the norm we're using for this first part, isn't changing, right? We're using squared loss for that first part. It's just what is the norm that we're going to use for the penalty on it. Yeah. The question is, for this term over here, will we ever use L1 loss? Like, could I ever replace that with the 1? And the answer is you could, but we probably wouldn't. I think there is a past exam question out there somewhere saying, what would happen if you did do that? Somewhere. And what happens to the residuals? Something like that. But you can look into that. Okay, cool. So this is a really quick picture I want to draw to sort of illustrate why L1 vector norms encourage some of the elements to be 0. And I'll come to the question in just a second. So why don't we draw this axis? And first, why don't we look at the vector 5, 0? Okay, that's terrible. Sure. 5, 0. What's the L1 vector norm of 5, 0? Well, it's the absolute value of 5 plus the absolute value of 0, which is 5. Great. And what's the L2 norm? Well, it's the distance of this point, of the end of this vector to 0, which is, the square root of 5 squared plus 0 squared, which is 5. Nice. Now, what if we look at 3, 4? Okay, that's not an accurate picture, but whatever. Look at the L2 norm of 3, 4. You get the square root of 3 squared plus 4 squared, which is also 5. But what happens if we look at the L1 norm of 3, 4? Well, that becomes the absolute value of 3 plus the absolute value of 4, which is 7. Okay? And so, again, this is not like a rigorous proof that L1 encourages sparsity. We can kind of see before, two vectors that have the exact same L2 norm, so that their endpoints are the exact same distance from the origin, the one that had an element that was set to 0 had a lower L1 norm. Does that kind of make sense? Great. Think there was a question? Yeah. Sure. Yeah. Yeah, so there's no, like, we essentially don't do that. So, like, there's no term for that, if that makes sense. All forms of least squares, I mean, it's in the title, right? Least squares, we're trying to minimize the square loss, if that makes sense. Yeah. Sure. For the first part, yeah. The first part, that's not going to change. It's just what we tack on to the end. Yeah. Cool. So now I think it's Neil's turn. Did you have a question? Yeah.
You said that L1 loss, which minimizes the norm of theta.
The L1 norm of theta.
The L1 norm. I'm confused how the L1 norm is going to be 3 plus 4. Because the norm is going to be like b beta dot beta squared root.
So you're saying you're not sure why the L1 norm, like if we use lasso, there's not a closed form?
No. I'm just saying, like, why is the norm, like, you were trying to, the question was that, you were trying to say feature selection
Sure.
with L1.
Yeah.
You said you're trying to minimize norm of lambda times norm of beta.
Correct.
Lambda times norm of beta squared.
Correct.
Right? But norm of beta, both those vectors are still positive. Right? It's beta dot beta squared.
It's the difference between, okay, so I guess I can show you this. Like these behave differently. Like one's not just the square root of another, if that makes sense. And what we're saying, and we're kind of just treating this like a black box, is that this first one encourages, like when you find the minimal solution using gradient descent or whatever, it turns out to be the case that a lot of these values will end up being equal to 0. And if a value is equal to 0, well, that's just the weight that it's putting on that specific feature. So it's essentially telling you don't use that feature. Does that kind of make sense?
Kind of. Yeah, I think it's just a definition.
Okay, cool. Yeah.
To effectively compare to don't have to square the L1 norm. Otherwise your second example doesn't make sense.
Okay, yeah, so that's a good question. Like why isn't this like 25? Yeah. So this is just L1 versus L2. What's used in the question is slightly different, and it's just sort of convention that we square the L2 one but not the L1 one. But the example still holds.
So wouldn't the L2 norm always be less than the L2 norm? Wouldn't the L1 norm always be less than the L2 norm squared?
I don't know if that's necessarily true. Okay. I think out of the interest of time, we probably have to move on. So I'll give it back to Neil for bias variance. He's still watching hockey.
Hey, it's hockey playoff time, right? Gotta enjoy that. Okay. Okay, so we're just gonna do a speed run through bias variance because we still need to get through logistic regression. So basically what this plot is showing, or what this image is showing, is you have like this dartboard, and as always, you're trying to get to the center. So essentially, so over here we see that we have low bias because we're pretty close to the center, but we have high variance, right? Because our predictions are scattered around. And over here we have high bias because we're far away from the center, and low variance, right? Because all our predictions are close to each other. And then this is kind of the worst situation where we have high bias and high variance. And our whole goal for like our models when we evaluate bias variance, our whole goal is to get over here where we have low bias and low variance, right? So let's just review a little bit about what bias variance is. So, and I think in lecture you guys didn't see this epsilon. So everything basically you have some test point, you have some point x. And in nature, you have a true value for that x, which is h of x. And essentially what this epsilon is, you don't need to worry about it because we didn't cover it this semester, but this epsilon is just some noise term. So like when you go to nature, when you get a value when you get a point in nature, most likely it's going to have some noise attached to it. So that's why we model it using this epsilon. But essentially our whole goal for our models is to get as close to the true value for that point x, right? So as we saw when we tried to minimize, we had this risk and empirical risk, and we tried to analyze certain aspects of that empirical risk. So we saw that in class when we did this derivation, that the empirical risk broke down into two terms. We saw the bias square term, and then we saw the model variance term. Okay, so basically we have this trade-off between we want to get as low bias as possible, but we also know that, as we'll see from the images as we move on, the lower bias you have, that tends to have more complex model variance. So your model variance actually increases. And one negative aspect of that is, we'll see one negative aspect of that is kind of like overfitting our model. So overfitting is essentially where we train our model so close to our to our training data, so that now when I go and predict on data that's out in the testing, so when I go predict on data that I've never seen before, I don't do as well, right? So my bias might be really good, but I'm not going to be very good in terms of predicting on new data. Okay, so now if we look at basically as what Suraj was mentioning about regularization. Regularization is meant to help out with this bias variance trade-off. So as we see here, we have this objective function for ridge regression. So we have the squared loss here, and then we have ridge regression, so L2 loss, or the L2. And as we see here is, as our lambda value increases, the model complexity decreases, right? The reason why our model complexity decreases is because this value over here is getting larger, right, as lambda increases. So as a result, we want to minimize this whole expression, right? So by minimizing this whole expression, we want this value here to necessarily be as smaller as possible, right? So we're kind of adding a penalty to the existing loss function to penalize it for being too complex. Okay, so in generally, as lambda increases, our model bias is going to increase, right? Because our variance is going to decrease. So as we penalize our model more and more, we're going to basically make our model less complex, but as a result, we're going to have a higher bias. Yes? The fundamental difference. So the question is, what is the fundamental difference between bias and loss? Yeah, so that's a good question. So if we take a look at what the bias term here is, you can kind of think about bias as, so we have this true value that we're trying to estimate, and what bias is estimating is, so if we take a look at what this term means, we're finding the expected value that like an expected model would predict on x. Okay, so the reason why it's an expected value of f(b) of x is because we don't know what training data we're going to get, right? I'm just going to give you a random sample of some data, and I'm going to call it the training data, right? So depending on what that random sample is, we're going to generate models that are different based on our training data. So what bias is measuring is, out of all possible models that you could generate based on some training data, how far are those predictions going to be on the average model compared to the true value? Loss is usually loss when loss is being measured directly on like your data set directly. So like, did I do well on this data point or this data point? Bias is more of like a kind of a theoretical concept where we're trying to find how well am I going to do on average for like an expected model sort of thing. Does that kind of make sense? Well, we know what y is, right? We don't know what h of x is. I mean, we don't know what the h function is, but I give you a point, and then in my training data set, I tell you what the value is for that point. Right? So like I give you in the beginning, I give you these sample points, and you know what yi is. Okay. Any other questions? Yes.
So, realistically, can you give me an example of like a model of F beta? And so essentially, we are, so H of X is basically the observed, right? The observed
H of X is the observed value, yeah.
And what is the explanation of F beta?
Yeah, so F beta is, for example, a linear model could be like beta 0 plus like beta 1 times x, for example. And so in this case, beta could be a vector, or it could just be like a single parameter. So F beta is, so in this case, right, we're given some sample points. So like, if I do this procedure again, I could have a different sample of points, right? A different set of training data. So what bias and model variance are trying to estimate is how well on average so bias is trying to measure like how well on average is my average model going to predict on this x value compared to the true x value. And then what model variance is predicting is, now I have this expected value that I would predict for like an average model. How well do each of the models do compared to that expected model? Okay. Yes. Can you repeat that? Sorry, I didn't. Yeah, so h of x is, so you can think of h of x as like the true model in nature for like what I'm trying to measure. F beta of x is my estimated model. Okay, because like I'm not going to get it perfect, right? I might have a model, like I might be using a linear model, but like the true model in nature might be like a logistic, like a exponential model or something. Okay, I'm going to move on just for time. Okay, so this is just the plot. You've probably seen this plot over and over again. But so what this plot is showing is as model complexity increases, our variance is going to increase, and our bias is going to decrease. Right? And usually the optimal value is right when they meet. So this is generally when we have low bias and low variance. And our test error, the reason why test error is above, the reason why test error is at the top is because as our variance increases and our bias decreases, our test error is going to increase too. Because the reason why is because as we talked about overfitting, so if I make my model really complex, my bias is going to go down because I'm going to do really well on my training data set. But when I go to evaluate it on test data, my test error is likely going to go up. Yes?
Does bias and variance always describe the training set?
Does bias and variance always describe the training set? Yes, usually they're about like the data that I'm given in terms of my sample points. Yeah. Okay. Yes? Yes. So when we say that variance, okay, so essentially what we're saying is, so low bias is how well we do versus like the true value, and our variance is basically out of all the models. So like for example, let's say I have some test point X, and I keep on, so let's say I give you some training data set, and then I give you another training data set, which is the same as the first one, except I take out a point, for example, and I replace it with another point. If my model has high variance, that means that the second data set that I give you is going to result in a completely different model than the first one I gave you, which as a result will give me a different estimate for some value x. So if that makes sense. So if I give you like a 15-degree polynomial, right, and I ask you to train it on like 10 points, if I give you like 9 of the same points and like one other point, it's very likely that your 15-degree polynomial is going to change quite a bit because you tried to fit your 15-degree polynomial exactly to the data. Okay, cool. So this is just an estimate, or this is just an image of polynomial regression with large d. So d is like the degree, and we have small degrees. So we see that, as we talked about, right, when you have a high degree polynomial, you have low bias because you're going to hit on points very close, but you have a higher variance, model variance, right? Okay. Okay, now let's quickly talk about cross-validation. So, as Suraj mentioned when he was talking about regularization, we have this lambda parameter, right? So, what cross-validation does at a high level is it takes our training data. So, we have test data that's out and we haven't evaluated on yet when we're training. Now, we split our training data into like a training set, more training data, and then a validation set. So, we take our training data and we split it into validation data. So that's what these things are, right? And the whole point of cross-validation is to find the optimal lambda value. Okay, so as it mentions here, cross-validation simulates multiple train test splits on the training data, and it helps us find the best hyperparameters for a model. Okay, and we'll see how we do that. So the general procedure for cross-validation is we split our data into training and test data. And for each training fold, so when we say a training fold, we mean like for each split. So like if I have 5-fold cross-validation and I have 100 data points, every single fold is going to have 80 tests. So for example, one way you could split it is I could split the 100 training points into like 80 training points and then 20 validation points. Okay, and if I do like 5-fold cross-validation, I'm doing that split 5 times. So I might split it into like the first 80 is the training data set, is training points. The last 20 are validation points. And then my next fold might be like indices 20 to 100 are my training points. And then indices 0 through 20 are my validation points and so on. Okay, and your whole goal is for each fold, you want to train on the training data, and then you get a score or an error on the validation data. So you can think of your validation data as like your pseudo-test data for that fold. Okay? So I train on my training data, and then I evaluate on my validation data. And then you repeat this procedure for different values of hyperparameters. So for example, for lambda equals 0.1, for example, I might do this 5-fold cross-validation and compute the training error for each fold. Right? And then for lambda equals 2, I'll do the same thing. Right? And our whole goal, and we'll see an example later on, but our whole goal is to basically choose the lambda that results in the smallest average error among all folds. So like, for example, I might have a table that says like fold number, and then 0, 1, 2, 3, 4, 5, and then lambda equals 0.1. So I might have some errors here. And then I might have, I ran out of room, but I might have another column that says lambda equals 0.2, lambda equals 0.3. And I repeat this 5-fold cross-validation for each lambda. And then at the very end of my procedure, I choose the column that has the lowest average among the... So I average the values in each column, and then I choose the lambda that resulted in the lowest average. Okay? Okay. So let's move on to a question. So this question is very similar to what we were just talking about. So basically, you're working with a partner to train a model with hyperparameter lambda, and you and your partner run a 5-fold cross-validation and compute the mean squared errors for each fold, and then value of lambda from a set of 4 candidate values. So they forget to send you the results for the last 2 folds, so the table below contains some mean squared errors for the first 3 of the 5 folds. So I'll give you some time to think about A and B, and then we'll reconvene in like 2 minutes. Okay, let's move on. Okay, so part A, your partner uses the full table containing data for all 5 folds to create a final model to use on test data. So given the information above, what can you conclude about the final model? Okay, so should our final model use lambda equals 0.4? How many people say true? False. Okay, good. So it is false. Okay. So just given the information above, obviously if I average together, so as we mentioned, we want to find the column that has the lowest average. So if I average these values versus these values and then these values and then these values, I don't want to use lambda equals 0.4. From here, I want to use lambda equals 0.2. Okay. Our final model, I'm going to make sure I don't check this. Okay, our final model should be trained on fold 1 since it achieves the lowest row average. So is that true or false? False, right? So we don't care about, usually we don't really care about row average because it's not really telling us anything. All row average is telling us is how well we did on fold number 1 for various hyperparameters, so for various lambda values, right? But our goal is to find the best lambda value, and that will be achieved by looking at the lambda value across all the folds. Okay, our final model should be trained on fold 2 since it achieves the highest row average. True or false? So how many people say true? False. Okay, yes, it is false. So it's kind of the similar reasoning for part B, where the row average doesn't tell us anything about how well the lambda values do. Okay, so it's none of the above. Okay, so part B, let's say we know the row averages for all 5 folds. Which of the following are valid conclusions we can draw? Okay, so we can determine which fold number to use for our model. Is that true? So how many people say true? How many people say false? Yes, that's false. Okay, because the idea is once we get our lambda value, we don't care about our folds anymore. Okay, we're going to train on the entire data with that lambda value. Okay, we can determine which lambda value to use in our model. Is that true? So how many people say true? False. Okay, so this is a trick question. So all we're given is the row averages. We're not given the actual column values. Yeah. Yeah. Sorry, I'm a troll. So I didn't write this question, so don't blame me. Okay. So if we're given all the column values for all 5 folds, then we can determine which lambda value to use. Okay. So the answer is none of the above. Okay. I'm going to skip these just for time. So let's just go to classification. So I'll give it back to Suraj.
This man doesn't stop watching hockey. Okay, classification. We have 19 minutes. You could probably finish most of this, but before I post these slides later tonight, I'll fix whatever typos there are, and yeah, we'll go from there. Okay, so when we get to classification, there's like this fork in the road, right? So what we've done so far, regression, was the problem of taking in, a set of data, and really we're just trying to create a model in which we would take in a point and predict some real number based off of it, right? So for example, we could, take in a student's, midterm 1 grade, midterm 2 grade, and their grades on the homeworks, and predict what we think their final exam grade would be. That's an example of doing regression. On the other hand, classification is the problem of, again, taking in a data point, but now we want to predict some sort of label. We want to predict, for example, whether or not a patient has a disease, okay? What type of dog we think this dog is, given this information about them, that sort of thing. Okay, we're trying to predict a discrete label as opposed to some real number output. Is that clear? And if you've taken the prerequisite data 8, this is not a new idea, right? In data 8, they talked about k nearest neighbors, which is also a classification technique. Okay, and so this is an example from the textbook. Suppose we have LeBron's shot data for a particular season. And suppose we have the distance from which each shot was taken and whether or not it went in. So the ones up here are the shots made. I guess here is not made. So notice these are our two classes, 1 and 0, which is something we will see a lot because most of what we'll do in this class is called binary classification. We're predicting if a point belongs to class 1 or 0. What we could do, if we didn't know about the existence of things like logistic regression and whatnot, we could just fit a line using OLS or ridge regression or whatever, and interpret the value as being the probability that the shot goes in. And if it's above some output, we'll say the shot does go in, and if it's below that threshold, we say it doesn't go in. But the issue is, the way we have OLS set up, the outputs could be greater than 1 or less than 0. But what do we know about probabilities? They're restricted to be in the range 0 to 1 inclusive. So this doesn't work that well. And so, just as a recap, we know for something to be a valid probability density function, all of the outputs have to be in the range 0 to 1. And the sum of all the outputs, or if you were talking continuous, the integral over all the outputs has to be 1. Okay, so essentially what we need is some function that takes in any real number and gives me out an output that's in the range 0 to 1. So give me any real number, the output is restricted to be in the range 0 to 1. And the function we choose for that purpose is the logistic function, okay, or the sigmoid function, okay? 1 over 1 plus e to the negative x. Okay, and it happens to satisfy the property that its derivative is it times 1 minus it. Okay, so this, I mean, you've definitely seen this before at this point, I would hope. Okay, and so now going back to standard linear regression, if we wanted to predict predict whatever we're trying to predict, so for example, a final exam grade, you'd look at the expectation of the output given a single test point. So here I'm using a little x, would be x transpose beta, where beta is those weights that we found by optimizing this thing. Okay, so we find beta by using the solution to the normal equation, and then I want to take a new point and compute x transpose beta, which is the output of this new point that I'm testing on. And now what we're going to do instead is use logistic regression. Okay, and our model is essentially of this form. The probability that our point belongs to class 1, right, given our test point little x, so we can call this our test point, is the sigmoid of x transpose beta, which, by definition, is 1 over 1 plus e to the negative x transpose beta. Okay, so the model I'm trying to fit is, give me a single point, the probability that it belongs to class 1, so the probability that y is equal to 1, is the sigmoid of x transpose beta. Now all we have to do is figure out some way to determine these betas. Okay? One thing I really want to stress, though, is that this output of the sigmoid function will be some continuous value in the range 0 to 1. Right? But what we want to do is classify the point as being either 1 or 0. Right? If I do this calculation and I get 0.6, for example, that's not a class, right? The classes we're looking at are 1 or 0. So in order to interpret the results of logistic regression and turn it into a classifier, we have to set some sort of decision boundary or threshold. So what we can say is that if the probability of our point belonging to class 1 is above p, and a standard example is probably 0.5, right? If the probability of our point belonging to class 1 is greater than or equal to 0.5, we will say it's in class 1. If it's below 0.5, we might say it's class 0. Is that clear? So the output of logistic regression is a continuous value from in the range 0 to 1. But in order to actually classify it, we have to pair it with the decision boundary. And I think that's something they talked about in lecture. You had a question?
Yeah. It might be a good question, but why is it need to transpose x? Isn't this the point?
That's actually a very good question. So the interpretation of this, so almost always, on their own, vectors are columns. Okay? So what we're saying here, in this context, little x is just a single data point that's written as a column vector. This is in opposition to big X, which was our matrix that contained all of these data points. But one thing you'll notice is that in this matrix, you'd essentially have to write each data point as a row. Okay, so that's something to keep in mind. But as I mentioned earlier, on the reference sheet that's posted on Piazza, the notation, again, this semester is a little confusing, and they used big X in both contexts. So they used it both as a data matrix, but also as an individual test point. So again, you have to be aware of what context we're using it in. And just to make it a little more clear, in the slides we use little x for a single point. We literally spent like an hour trying to figure that out right before coming here. So it's not a stupid question. Okay, so any questions with what we just talked about? Okay, and so this is the output of the sigmoid of x, and I'm sure this is something you've seen before. Cool, and so for example, pretend this is the output using our set of betas. What we need to pair this with is some threshold. So we say, well, if our predicted value is above this red line, we'll say our point belongs to class 1. If it's below the red line, we'll say it belongs to class 0. Is that clear? And I just sort of drew this arbitrarily, but you get the idea. Great. And so now is the question of what's the loss function for logistic regression? Okay, and this is what's known as the cross entropy loss. And sort of the derivation of it comes from information theory. So if you really care, you can take EE229A, but probably not necessary. And so for now, let's just think of it like this. The average cross entropy loss is of this form. Okay, and for probability distributions, which is what we're trying to predict, it's preferred over L2 loss for a number of reasons, which they probably talked about in lecture. Sensitivity to outliers with L2 is probably one of the things they talked about. Okay, and this is also, at least for our purposes, referred to as log loss. So for us, those mean the same thing. Okay, and this you can't really determine it numerically, analytically, so we'll use a numerical method, such as gradient descent, to find the optimal beta that minimizes the cross entropy loss. Okay? So any questions with this? Yeah.
So why are we using this formula compares to the one in the book, where it has the natural loss on both sides, and natural 1 minus yi?
So you're saying the thing you saw in the book looks something like y log, like pi log pi, and then 1 minus y log 1 minus pi, something like that, right? Because we know our probabilities are outputs of the sigmoid function, this is just a more simplified version of that. So you might have seen a different expression that involved 1 minus y and things like that. That's the exact same thing as this. It's just a more simplified form. Okay, and we just use the fact that you take the log of a sigmoid, and there are some nice properties with that, right? Like you take the log of 1 over 1 plus e to the negative x. Well, you can use log rules to separate that, and so you get a little more simplified form over here. Yes?
We were told that if you're setting a decision boundary, you might choose one like the higher decision boundary, for example, if prediction one like means something more. You don't want to predict. When you predict one, you want to be really certain about it.
Sure, yeah. So
Is that the same thing as weighting? Is that the same thing as weighting an incorrect classification for one higher in the loss function? Would that be the same thing? And then minimizing that?
So your question is the process of determining a good threshold over here related to figuring out beta over here? I want to say no, because there's no room for adding a hyperparameter, at least the way this is phrased right now. Like this is the optimization problem, and there will be a single optimal beta to this. And then depending on the context, right, if you want to minimize the number of false positives or the number of false negatives, you can set your decision boundary in that way.
There's a question on the guidance that says if you penalize like false positives more than false negatives, you end up with like this what you would end up with.
Can we talk about that after this? Cool. Were there any other questions? Okay, here and then in the back, and then we'll move on.
So in this formula, yi is a number, a constant,
Correct.
and then xi is a vector, and beta is basically a vector.
Correct.
So we do dot product between xi and beta, but if
Yep.
we do the regular implementation with yi.
Yep, correct. So good. So here, yi is a scalar. Xi is your feature vector, or like your data point, I guess you can say, feature vector. and beta is your weights vector. And the most recent discussion has a question where you walk through determining the empirical risk or the empirical loss for a single point, and you get to see all of those dimensions. Question in the back? So your question is, why are we using maximum likelihood estimation? Okay, so part of the answer is maximum likelihood estimation is something they've chosen not to cover in this class. And I think there are ways you can arrive at the same loss function and the same model using maximum likelihood estimation. That's sort of outside of the scope of this course. Okay, I'll move on just because we only have about 6 minutes left. Okay, then there's the idea of linear separability. Okay, so the whole point of doing logistic regression is because there's a little bit of uncertainty, right? We need to model something with probabilities. But if we're able, like if you look at your data and there's clearly one group of points belonging to one class and another group of points belonging to another class, then you don't really need to use logistic regression, right? You can just say, I'll put my pencil here. Everything to the left of this is red and everything to the right of this is green. Why would you need to do logistic regression there? Okay, and so the first example is linearly separable because I can essentially do that. But in the second one, there's no point at which I can draw a line and say everything to the left is in one class and everything to the right is in another. Is everyone okay with why the first one's linearly separable and the second one isn't? Great. Okay. So there's actually a question in this week's discussion that, or last week I guess, which was intentionally misleading. So it showed you a plot like this and it said your friend is going to draw this line in black. Is this data linearly separable? And the answer is no. Right? And it's because you have to look at the formal definition of what it means for data to be linearly separable. A set of d-dimensional points is linearly separable if and only if you can draw a d-1 hyperplane to separate those points. Okay, so what does that even mean? Well, so the first question is, what is d in this case? It's 1, because our values only have one dimension. Right? X is a simple scalar, it lies somewhere along the number line. The reason we see y is because y is the class label. So when we're looking at the dimension d, we're looking at all of the coordinates other than the class label. And apart from the class label, our value of d here is 1 because x is just a single value. So our points are one-dimensional, and the question is, can I draw a degree 0 hyperplane? Okay, and just a degree 0 hyperplane, so a degree line since we're working in 2D, is something of the form x is equal to a. A degree 1 would be something like y is equal to ax plus b. Okay? And so, since our data is of degree 1, we need to be able to draw a hyperplane of degree 0, which again is just some vertical line, saying that everything above or to the right is in one class and everything below or to the left is in another. And I can't really do that anywhere. Okay, that was bad, but you can't really do that anywhere here. So this data is not linearly separable. Yes? So is your question, how do you interpret this in higher dimensions? Let's see if yeah, great. So this is an example of where our points actually have 2 dimensions on their own. So we can call this the x1 axis, this the x2 axis, and then on top of that they also have a class label, 1 or 0. And so this is a case where d is equal to 2, so we're looking for a degree d-1 hyperplane, which is something of the form y is ax plus b. And in the left case we're able to do that, in the right case not so much. Does that sort of make things more clear? Cool, so that's linear separability. And then just to wrap things up, we have the idea of precision and recall. Okay, so precision and recall are 2 different ways of evaluating the effectiveness of your classifier. Okay, so we have the idea of true positives, so things that actually the class was actually equal to 1 and you said it was 1, right? True negatives, when the class is actually 0 and you said it was equal to 0. Then there's false positives and false negatives, the ones you don't want. Right? So false positives are kind of like false alarms. Right? You said that the value is true, but it's actually false. And false negatives are the ones you don't want when, for example, you're trying to detect a disease. You say the person doesn't have the disease, but they actually do. Okay, so precision and recall are two different ways of evaluating the effectiveness of a classifier. Alan actually told me a great way to remember which one is precision and which one is recall. Precision starts with a P, and all of the terms in it involve a P. So that's a great way to remember it. Okay, so all terms involve P. Great. And so this is a picture. You've probably seen this before. And so we could go through an example. We're trying to classify pictures of LeBron. You test it on 23 images. There are 12 images of goats. And you can go through and calculate the true positives, true negatives, false positives, and false negatives of this. But I think we're running out of time, so we'll probably end it there. We'll post the slides and the webcast pretty soon after this, by tonight, and we'll fix the typos. But feel free to come up right now if you have any questions. And good luck tomorrow.